Hello everyone, my name is Liu Jiayi, and my student ID is MAT2409019. Today I will give a presentation on equivalent definition of the continuity. And first, I will explain the meaning of the continuity. Then I will introduce the epsilon delta definition, and next I will discuss the open set and closed set definition. After that, I will expand the sequential definition. Finally, I will show why these definitions are equivalent and give two simple examples to show you. Let me begin with the intuition. In calculus, we often said that a function is a continuous if its graph has no sudden jump. In simple words, if the input change only a little, then the output should also change only a little. But in mathematics, we need a precise definition. For continuity, we can describe the same idea in several languages: epsilon, delta, open set, closed set, sequential, sequence language. This definition looks different, but they express the same concept. Now, I will introduce the epsilon delta definition for you. Let f be a function from a to real numbers, and let a be a point in big A's. We said that f is continuous at a if for every epsilon greater than 0, this exists the delta greater than 0 such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus f of a is less than epsilon. The mean is clear. If x is close enough to a, then the f of x is close to f of a. This is the most direct and classical definition of the continuity in analyze. Then, now let us look at a short example for you. Consider function of x fx equals x squared. To show continuity at a, we look at the absolute value of x squared minus the squared values equals to the absolute value x minus a and absolute value x plus a. If the absolute value of x minus a is less than 1, then the absolute value x plus a is less than 2. Absolute less than 2, absolute a plus 1. So the whole expression is less than the absolute value of a minus a times 2, absolute a plus 1. Therefore, if we choose delta to be a minimum of 1 and the epsilon over 2 absolute a plus 1, then the expression become less than epsilon. So f of x equal x squared is continuous at a. Next is the open set definition. A function is continuous if for every open set v in real numbers, the pre-image of v is open in A. In other words, open sets stay open when we pour them back through the function. This is an important viewpoint in topology. If it is more abstract than the epsilon delta because it focuses on the set instead of distance. Now we have a closed set definition. A function is continuous if for every closed set C, the pre-image of C is closed in A. This is an equivalent to the open set definition because a set is closed exactly when its complement is open. Also, pre-image work well with the complement. So the open set and the closed set definition are really two forms of the same ideas. You can see here. And let us look at the sequential definition. We say that f is continuous at A if for every sequence x sub n in A. Whenever x sub n converge to A, the sequence f of x sub n converge to f of A. This definition is often very convenient. If we want to show that a function is not continuous, it is often enough to find one sequence approaching A for which f of x sub n does not approach of A. Why the definition agree? Now I will explain the why this definition agree. For a function from A to real numbers, epsilon, delta, continuity, open set, closed set, and the sequential continuity are all equivalent. The logical is that epsilon delta continuity is equivalent to the open set continuity. Open set continuity is equivalent to the closed set. And the epsilon delta is equivalent to the sequential continuity. So if one definition holds, then all the others will hold as well. This shows the continuity is one concept viewed from different angles. Then here is a simple example of a continuous function. Let fx equal 3x plus 1. This is our function, and we use epsilon delta. We have the absolute value of x alpha f of x minus f of a equals 3 times absolute value of x minus a. This is the function. So if we choose delta equal to epsilon over 3, then the continuous follows immediately. Using a sequential definition, if x sub n converge to A, then the 3x sub n plus 1 converge to 3a plus 1. So the function continue on the real numbers. Okay, you can see here. Next example. Finally, let us use the this continuous function, and my function is here. Define the function of x to be the one when x greater than 0, greater or equal to 0, and x when x is less than and 0, x less than 0. This function is not continuous at 0. Take the sequence x sub n squared equal to negative 1 over n. Then the x sub n converge to 0. But every term is negative. So f of x sub n equals 0 for all the n. On the other hand, f of 0 equals 1, so f of x sub n does not converge to f of 0. Therefore, the function is not continuous at 0. This is our next example of the discontinuous function. And here's my conclusion. To conclusion, the four definitions of the continuous look different, but they describe the same mathematical ideas. The epsilon delta definition is useful for directly proof. The open set and closed set are important for origin. The sequential definition is often the easiest one to use in examples. So by learning this sequential definition help us understand the continuity more deeply. Thank you for your listening.